Large language models are increasingly deployed as goal-driven agents, tasked with generating actions to navigate complex external environments, like compilers, operating systems, and web APIs. When an agent fails a task, the standard protocol for improvement is reinforcement learning. The agent takes an action, the environment returns a reward, and the system updates the neural network's weights via gradient descent. Applying that standard protocol to a frontier LLM requires enormous compute. Running millions of training samples and calculating gradients across hundreds of billions of parameters makes continuous fine-tuning financially and temporally prohibitive. Because of this computational bottleneck, engineers have largely abandoned weight updates for deployed agents, relying almost entirely on static, in-context examples to guide behavior. Reflexion proposes an alternative: abandon weight updates entirely. The model's internal parameters remain frozen. Delta theta equals 0. Instead, the agent is reinforced solely through linguistic feedback. Reflexion parameterizes the policy as a combination of that frozen LLM paired with a trainable episodic memory buffer. To achieve self-improvement without a massive GPU cluster, the system learns by editing its context window instead of its underlying mathematics. When an agent executes a long sequence of actions and eventually fails, the environment returns a simple scalar or binary penalty. That bare number cannot identify which specific step in the sequence caused the failure, the classic credit assignment problem. A traditional neural network uses backpropagation to trace that scalar error backward through its layers. A frozen LLM cannot do this. The solution is a semantic gradient. The system amplifies the minimal scalar reward into a high-resolution verbal critique, replacing the mathematical vector of a standard gradient with a concrete language-based direction for improvement. This critique requires a specific anatomy to be useful. It must explicitly name the specific action that triggered the failure, and then propose a distinct counterfactual alternative for the agent to use on the next attempt. This mimics few-shot human learning. When a person fails a complex task, they rarely adjust a mathematical weight. They reflect on the failure, identify the specific mistake, and write a mental note to guide their next attempt. Reflexion forces the system to translate sparse environmental feedback into actionable human language before it ever enters the agent's context window. Algorithm 1 of the Reflexion paper formalizes this process using a modular triad of 3 distinct models operating in a closed iterative loop. The first node is the actor. It observes the current state, reads memory, and outputs an action trajectory. The second node, the Evaluator, observes this trajectory and calculates a single scalar reward from the environment. That single scalar, often just a pass or fail, is the only external learning signal the system extracts from the environment. The third node is the self-reflection model, acting as a critical amplifier. It ingests the trajectory and sparse reward, locates the specific error, and generates a verbal critique proposing an exact counterfactual for the next run. This critique is appended to a long-term episodic memory buffer attached to the actor. To prevent overflowing the context window, this buffer is capped at 3 experiences. As a new critique enters, the oldest drops out. The only training step occurring between trials is this simple append operation. Complex policy optimization is happening entirely in context, without altering a single weight. To measure the effectiveness of this triad, researchers tested it on AlfWorld, a sequential decision-making benchmark comprising multi-step household tasks. Standard React agents fail here by falling into hallucination loops. They falsely conclude they possess an item they don't have, trapped trying to use it. The Reflexion Evaluator intercepts this failure mode using a simple heuristic. If the agent repeats an action for more than 3 cycles, or exceeds 30 total steps, the run is terminated and a reflection is triggered. This line graph comparing trials 1 through 12 tracks the results. By distilling long failed trajectories into persistent self-hints, the reflection curve smoothly completes 130 of 134 tasks. The React-only baseline halts entirely at trial 6, trapped inside a 22% hallucination rate. The Hotpot QA benchmark isolates the mechanism, testing if an agent achieves similar gains simply by retrying the prompt without generating explicit reflections. The ablation data shows that refinement-only baselines fail to probabilistically improve across retries. Simply rerunning a prompt does not solve a previously failed question. Generating and appending the verbal critique provides a 14% absolute accuracy boost, correcting mistakes even when the agent is denied access to ground truth answers. Retaining episodic memory alone is insufficient. Generating a counterfactual semantic gradient is the exact mechanism required to pull the model out of a local minimum. The framework's absolute reliance on its evaluator is exposed in code generation. On the human eval benchmark, the evaluator consists of unit tests written by the LLM itself. This comparative chart tracks the performance pipelines. On the left, utilizing this self-generated test suite, a frozen GPT-4 model leverages Reflexion to jump from an 80% baseline to a 91% pass-at-1 accuracy on human eval. Yet, the exact same architecture on the MBPP Python benchmark yields no significant improvement. Populating the right side reveals the mechanical difference. The self-generated tests for MBPP produce a false positive rate of 16.3%, drastically higher than human eval's 1.4%. False positives destroy the reflection loop. When a flaky test suite passes an incorrect block of code, the evaluator falsely tells the agent its solution is perfect. The reflection cycle halts prematurely, and the error is permanently locked in. Because the model's weights remain frozen, Reflexion can only learn what its evaluator can detect. The agent's performance ceiling is violently dictated by the diagnostic accuracy of its oracle. We see the absolute failure limit of this framework on the web shop e-commerce benchmark. This spectrum bar maps evaluation signals. On the left, exact match or unit test grading provides sharp, reliable rewards. On the right, environments like web shop require navigating extreme natural language ambiguity, severely degrading the evaluator's ability to provide a clean scalar reward. Without a precise reward signal, the self-reflection model generates useless, disjointed verbal critiques. Consequently, agent learning flatlines completely after just 4 trials. The verbal reinforcement learning paradigm offers a direct trade-off. It successfully bypasses the computational bottleneck of massive fine-tuning runs, but it transfers that exact burden directly to evaluation engineering. To build a self-improving LLM agent today, success no longer requires massive GPU clusters for weight updates. It requires architecting a flawless evaluator to supply the words.